So I want to take this particular moment to talk about disentanglement because it's a term that is used a lot when we talk about variational autoencoders, and also very recently in the field when we're discussing more complex deep learning algorithms which try to disentangle features. And I have looked around for a definition of disentangled features, and there's actually a lot of different definitions out there. And it really depends on the algorithm that you're picking up, and usually within the paper itself that goes along with the algorithm, they've kind of defined what they mean by disentangled features. But one way to kind of capture essentially what disentanglement means is the idea of having features which are independent from one another. So when you have a latent code, for example, we want each encoding to be really encompass only one property within our image. So that if we have, say, images of people wearing clothes, if we change something about their body dimensions, so here's a really nice example where they say if we change the length of the left leg, we want it to be strongly dependent on the length of their right leg, but you don't want the clothes to change or anything like that. You want it to learn where it's important to have dependence and where it doesn't need to have dependence, and kind of adjust accordingly. And there's some really nice there's really nice GIFs and images online which show you examples of, say, circles within a box and kind of separating out the colors of the sphere from the box it lies within, and how certain features in a certain context need to be independent in order to move about in a 3D space. So it's a really nice term, but it does encompass a lot of different types of disentanglement. Now, the benefits of having disentangled representations is quite high in a lot of different situations. So, for example, I came up with one example here where we have a driving simulation. So realistically, if you were training a model for driving purposes, you'll have a training set which encompasses quite a wide range of driving situations, but there's not really any way to capture all possible situations. You know, driving will change depending on the country you're in. It will depend on how many people you have within a city, the population, and you'll get freak conditions where you know, accidents will happen or something unexpected will happen as well. So if the weather changes, we want our self-driving car to be able to adapt accordingly and kind of adjust accordingly. So those are kind of independent features from the driving component. Another example is the one we talked about, where if we wanted to change only one component of a person who's within an image, say make them taller, we don't want other properties to change along with it, such as the clothing, or say if they're holding an umbrella or something. That should all still remain the same because they're independent of the person themselves. So one such technique for creating disentangled features is indeed variational autoencoders, and they do that to some level, create disentangled features. And we saw that with the examples earlier, and we saw that with the loss function itself and how it kind of differentiated between features. But we can kind of enforce it to learn more in disentangled features very simply by adding a weighting term for the regularizer. So this is beta here. And this algorithm itself is called betaVAE, and it's a very simple modification to the original VAE. So when it's equal to 1, it's the same as our variational autoencoder, but if it's greater than 1, we can really enforce some additional constraints to that latent space even further, such that we get disentangled features. And when we do our practical session, if you manage to get through the variational autoencoder component, I would highly recommend trying out the betaVAE as well and really seeing what kind of changes that makes to your data. And I'm not going to go into these today, but there are also other variational autoencoders which are modifications of the original one. So this one here, VQ-VAE, it creates a latent discrete codebook. So that the codebook has 2 dimensions, and it could be of any length and any height, so we're not restricting it to a Gaussian unit distribution anymore. And we have a TD-VAE, which is works particularly well with sequential data, which I'm sure many of you will be interested in because you work in natural language processing and so on and so forth. So these are all worth checking out. And on the reading material, there are links to many other adaptations to VAE as well. So I don't think we could talk about generative models without touching on GANs as well. And one real difference between GANs and the variation autoencoder is that we, instead of our encoder decoder components, we have 2 different, very different components indeed. So we have our generator and our discriminator. So the purpose of the generator is to create new images, which is similar to our decoder, I guess, in that manner. However, we also have a discriminator, and the discriminator is producing some sort of output as to whether this image is fake or real. So we have a generator which is generating simulated images, so fake images or text or volume or whatever kind of data we're working with. And the purpose of the discriminator is to take one image or one data instance from our generator as well as another instance from our training set, and predicting which one of those are fake or real. And the idea is that if it's finding it very difficult to tell the difference between fake or real, it's actually learned a very good representation of the data itself, which is a great way of building an architecture which models data efficiently without the need for labels. So this is kind of a graphical representation of a GAN. So we have our random noise going into our generator here, and these are all weights that are updated for this particular task, recreate images containing digits. And then it goes through a discriminator, which also receives information from our training set, and the output from here is real or fake. There's 2 labels. And through the loss function that's defined within GANs, which I'm not going to talk about today, all of these weights get iteratively updated, such that next time a random noise goes through a generator, it should be able to give us something similar to what it last saw within the training set, and thus create a really good generative model. So this kind of architecture does rely on our training set, again, having many similarities to our test set later or our test environment. So it's important to take that into consideration when you use such an architecture. Yeah, if it sees something that it's never seen before, it would have problems with encoding that information or modeling it within our generator. So during the Lunch and Learn, there was a question about text. I'm happy to say that actually a lot of the techniques that I talked about today are also applicable to text. And I want to start off with a very, very simple version of I would say an autoencoder, but for text data, and it's one of the models that are in Word2Vec, and it's called the skipgram model, and is shown here. And the purpose of the skipgram model is to take a word or a couple of words or triplets of words and create a one-hot encoding to represent those 2 terms together with some sort of context information. And so not only are you encoding the words, but also the coupling of words or the relationships between 3 or more words, and so on and so forth. And then the output is the prediction as to what should go with that, with the target word, target text that you've provided. So say, for example, I gave the word "the" to this model here. A high prediction that would come out the output function, if trained appropriately, might be the cow or something similar. The cow jumped over the moon, because it's learned something similar to that architecture. Learned something similar to that particular term within the training set. So it's a really nice way of capturing context information within natural language, but without having to model something very deep or very complex. And I would highly recommend looking at this particular link here, which is a link to what is called an embedding projector, because you can actually see a word tovec in a high dimensional space and kind of zoom in and out and really see the clusters. And you can see here that you can use different mapping functions in order to see this particular one-hot encoding in multiple ways. So it's a great way to kind of look around this data set. And not just for autoencoders, but also for generative models as well. There's definitely been some inspirations using not just VAEs, but also GANs, and combining that with recurrent neural networks, which you'll see here. So this is a traditional recurrent neural network architecture where you have inputs, internal states that need to be updated. So these are LSTMs here, but you can have GRUs and other types of internal state functions. And then once updated, that internal state gets passed to the next time point, and then a prediction is made there. So these are all the outputs from each time step as well. So you can see here, this looks very familiar to what we saw earlier. We have our mean and variance of our Gaussian representations, and we have our encoded representation of Z here, and that gets passed to the decoder component. So this is actually great for sentences or data which can't be captured in, or relationships that can't be captured in just a couple of words, or even triplets or quadruplets of words. And I've also given the reference to the paper which used this particular technique as well. So feel free to look at that as well. So you can really see that we can use some of the techniques and some of the general ideas from variation autoencoders and autoencoders and apply them and adapt them to your purpose as well using other techniques in the deep learning field. So that kind of wraps up what I was going to talk about today about autoencoders and generative models. I want to finish off with a couple of slides just summarizing exactly when to use autoencoders and generative models. So here I'm going to do this for every single week right at the end, just a list of pros and cons, and we can add to this and take away things in our discussions. But I'd like to, by the end of the 3 weeks, to have a list of all the techniques that we've been through and pros and cons for each. And so here for the autoencoder, we know that it's a simple architecture. We know that we can stack it and make it more complex as we need to. And also because of its simplicity within the latent space, it's very intuitive. However, because it's greedy and because this latent space is kind of left to roam free, it may not work as well as we want it to work, and it's not really modeling the data or anything. It doesn't have an idea of what's happening within the training set as a whole, but rather it's going batch by batch and optimizing by what it sees in every single batch rather than as the whole training process. Also, interestingly, this reconstruction may be ideal for some tasks, but it may not be ideal for other tasks. So it's really constraining the autoencoder to perform the optimization in a very specific way. The generative model, on the other hand, actually has this global training property. So it is really looking at the entirety of the training set and trying to model a representation using a series of unit Gaussians which represent the data itself. And as such, it tends to perform better than autoencoders and gives us something sharper, some sharper reconstructions as a result. However, that does come at a price, and that price is we've made it more computationally expensive. And because of those more parameters that we've added, we've increased the complexity of our models, and arguably we may need a little bit more data in order to tune those weights appropriately to perform the reconstruction task. And those are all things that we need to take into account. Not only that, but also what kind of computational power you have on hand as well in order to train and model these neural networks. So next week, what we're going to look at is actually taking the variation autoencoder, which we took today, and taking it one step further and modifying the loss function to perform deep clustering. And these are a really nice family of unsupervised learning techniques. And what I like about it is it does that global training in that it learns something about the entirety of the data itself. And it gives us two outputs rather than just the one. So it may reconstruct the original input, but it also gives us clusters as an added bonus and without needing additional labels as well. So we'll look into that a little bit more detail next week. For the practical session on Thursday, what I'll do is for the first half hour or so, I'll do a quick recap of this material. I'll have the slides on hand as well. So if you had any questions about any of the slides you've seen, please bring them along. Also bring along your laptops because we'll be coding in Colab, and our task will be to build a variation autoencoder from scratch in PyTorch, and that'll give you a really nice way to get familiar with PyTorch in a very simple and easy manner. If you've already used it before, we can definitely take that a little bit further. As I mentioned earlier, look at betaVAE and also how to visualize VAEs as well, because ultimately we do need to look at validation metrics and evaluation metrics for variation autoencoders. And currently, really the only way to see how well it's doing is to visualize the encodings themselves in the latent space and see if it's doing anything intelligent. So we can look into that as well. And that is it for today. Thank you very much for listening. Yeah, I'll see you on Thursday.